So a field F is algebraically closed if every non-constant polynomial with coefficients in your field has a root in the field. So another way of saying that F is algebraically closed is that F has no, so alternatively, F has no non-trivial algebraic extensions. No extension field of the form F adjoined an algebraic element alpha. Okay, so let's do some examples. It's easier to show a field is not algebraically closed, so let me give some examples of fields that are not algebraically closed. So the rationals, the reals, and a field like Z5. These are three examples of fields that are not algebraically closed because I could show you polynomials in each of these fields that don't have a root in those fields. So for instance, I could do x squared minus 2. That's a polynomial with rational coefficients, and it has no rational root. The reals are not algebraically closed because of the polynomial x squared plus 1, for example. This has no real roots. And Z5 is not algebraically closed because you can maybe consider the polynomial x squared plus x plus 1. You could verify that if you plug in 0, 1, 2, and 3, and 4, and for x, you don't get out a multiple of 5. So those are examples of fields that are not algebraically closed, but the best example of a field that is algebraically closed is the complex. So here's a theorem. This is actually the fundamental theorem of algebra. The complex numbers C is an algebraically closed field. Meaning that every polynomial that has complex coefficients has a root that is complex. So I will show you why this is true. So here's a proof. I'm going to not verify every little detail. My goal here is just to give you a really good intuition of why this is true, but I won't nail down every single possible little detail. So this I'm going to say is a sketch of the proof. So I'm going to begin with Euler's formula. Euler's formula says e to the I theta is cosine theta plus I sine theta. That's a well-known fact, Euler's formula. So as theta ranges between 0 and 2 pi, so I'm going to let theta go from 0 to 2 pi, this is a circle in the complex plane. So what I mean by that is, let's say you have a little complex plane here. So there's my real axis R, there's my imaginary axis I. I could draw a little circle of radius 1, like this. So that's a circle of radius 1. So there's 1, up here would be the complex number I. As theta ranges from 0 to 2 pi, you traverse this circle once in the counterclockwise direction. Okay. So then I could look at, so then I could look at r to the e to the I theta power raised to the nth power. So what is this? So this is equal to r to the n e to the I n theta power, and that is r to the n times cosine n theta plus I sine n theta. So as theta ranges between 0 and 2 pi, this r e to the I theta to the nth power is a, well, maybe I should say, is a circle of radius r to the n traversed n times. So the radius of the circle is r to the n because I have this r to the n out in front. And then the n's inside the argument of cosine and sine just allow you to go around the circle more than one time, n times. So here's my complex plane again. Now I've got a circle of a radius r to the n. So let's say this is my circle of radius r to the n. Starting here, when theta is equal to 0, I go around the circle n times. So 1, 2, 3, and so on. Okay, so that tells me what this term looks like. So I'd like to prove that the complex numbers is an algebraically closed field. To do that, I'm going to take a polynomial, let's say f of x, to be an x to the n power all the way down until I get to a1 x to the first plus a0. This will be a polynomial with complex coefficients. And my goal is to show you why this polynomial has a root that's complex. So here's the thinking. If I plug in, so thus I'm going to plug in, instead of x, I'm going to plug in this complex number, r e to the I theta. Any complex number can be expressed in this form. And if I put this form of the complex number in for x, I get an r e to the I theta to the nth power plus a bunch of things all the way down until I get to a1 r e to the I theta power plus a0. Now, if r is equal to 0, then all of these terms go away, and I'm just left with the constant a0. That's some complex number. So let me draw you a picture. So here is maybe the complex plane again. There's a real axis, there's an imaginary axis, and I have some point here, the complex number a0. That's the value of the function f when r is equal to 0. So here's a picture of what you get when you plug in r equals 0 into this function. Now, if you draw a picture of what this function looks like as theta ranges between 0 and 2 pi, so let me say as theta ranges in between 0 and 2 pi, you get the following picture when r is 0, and you get the next picture when r is super big. So if r is a large number, like a billion or something like that, this polynomial will have behavior that's dominated by the largest term. So I'm saying if you stick in a very, very large number for r, like a trillion, this constant, a0, this last term, doesn't affect the behavior of the polynomial as much as the first term. In fact, r to the highest power dominates the behavior of the function f if you have a polynomial like this. So if r is large, then the polynomial behaves just like this highest degree term. And we've seen up here that this highest degree term is a circle of radius r traversed n times. So I need to draw approximately n very large circles of radius r to the n times an. So I get there. I tried to draw n big circles. Now I wasn't careful to draw the circles exactly perfect, because I still have these lower ordered terms that might give me some wobbles in my circle and so on. But still, if r is large, I'm approximately getting some very big circles. The key observation is eventually the circles, as r grows, as r is big enough, the circles will contain the origin 0, 0 inside of them. So this middle point in the complex plane will eventually be inside of this drawing of big circles. So here's the proof of the fundamental theorem of algebra. I'm going to imagine theta ranging between 0 and 2 pi, and then I'm also going to imagine the r value starting at 0 and increasing, growing, until I get a picture of a bunch of big circles that have the origin inside. So as this r changes, it grows from just being a single point in the complex plane to being bigger circles. So in the middle here, r not 0 and not big enough yet, there's going to be a curve that's traced out by my function that will hit the origin. So I tried to draw a curve. This is r in the middle, I guess, before it gets to be n large circles. It's going to grow, and eventually have a curve that just touches the origin. And when this curve touches the origin, the function f has a root, because that says there's a value of f you could plug in here, some complex number that you could plug in to get out 0, 0, 0 in the complex plane. Now this proof is easier to understand when you see kind of a video of what's happening as r changes. Now I'm going to show you images of this in Mathematica in our next video, so please check that out because I really think that'll help understand the proof. But anyway, that's the reason I'm going to say that I'm done for this video for now. That's the reason why the fundamental theorem of algebra is true. Check out my next video. That'll really hopefully make this argument more clear. Okay, I'll see you then.